Okay, so when you talk about higher order derivatives, what you're really talking about is iterating the limit process, and that's what it says here. And really what that means is if you pass a function into this definition, you end up getting its derivative. And if you take the derivative, which is also a function, and just fire it right back into that definition, right back into that formula, what's going to come out is a higher order derivative. So let me spell that out a bit. So for example, the second derivative of a function f is defined as follows. So really, we're going to apply the definition of the derivative, but instead of applying it to f, like if I was going to apply it to f, this is what it would look like. I get the limit as h goes to 0 of f of x plus h minus f of x all over h. But what I want to do here is I want to actually apply this to f prime, not f. So now what's going to come out of this is not f prime of x, what's going to come out is f double prime of x. Okay, so that's the definition of the second derivative of a function f. Really what you're doing is you're taking the derivative of the derivative. Right? So one more time just to look at this formula, you can confirm that what we've written down here on the right-hand side of this equation is exactly what you would get if you applied this limit definition, but instead of f, you did it with f prime. Right? So that's where that's coming from. Okay, so that's referred to as the second derivative of f, and you can write it in several different ways. So just some more notation, which is really just going to be the higher dimension analog of the notation I introduced on the previous page. But if I want to talk about the second derivative of a function y, when I write y as a function of x, I can write y double prime. That's one way to write it. I can write f double prime of x, which we just wrote above in the actual definition of the second derivative. That's another way to write it. And now if I want to write it in Leibniz notation, it's kind of like the dy dx, but I write it like this. I'll write d squared y over dx squared. And the reason you write it that way is not always obvious at first, but if you read it out loud in a very specific way, it suddenly becomes clear why you'd write it that way. So the way you read this is take the derivative twice of the function y with respect to x both times. That's how you should interpret those symbols. And if you interpret them that way, then it kind of seems reasonable why you would write it that way. And you can also write it in operator notation, which looks similar but yet is a little bit different. Basically, you just separate the y from everything else, and you get d squared dx squared of y, and then just writing y in square brackets, right? So take the derivative twice with respect to x both times of the function y. That's what this notation means. And then I can write it the same way with f of x if I wanted to. I could write it as d squared dx squared of f of x. Okay, so those are 5 different ways you can write the second derivative. And there's no reason you'd have to stop at the second derivative. If you wanted to take the derivative again, you could. And you would just do it in the same way. You would just keep iterating the limit process. Maybe you would plug f double prime in here, or f triple prime, and that would give you the fourth derivative. You know what I mean? You just keep on plugging it into the limit definition over and over again as many times as you like. There's nothing really stopping you. So in general, let's write this one more time, but for a general n greater than or equal to 1, where n is really representing the number of times we take the derivative. So that's what we're saying here. We can generalize this notation to higher derivatives by repeating it any number of times. So really there's an nth analog for each one of those pieces of notation. So if I want to write in prime notation, like I'll slide down just so we can compare them to these 5. So for this one, if you want to count the apostrophes, that's usually what you do. But as soon as you get past like 3 or 4, by the time you get to the 4th one, usually you'll just put the number in brackets. So for the nth derivative, I'll just put y and then put n in brackets as a superscript. That just stands for the nth derivative of the function y. And you do the same thing for f, because really what happens is as the number of derivatives you're taking gets higher, the number of apostrophes to count gets more and more annoying to have to keep track of. Like, this is pretty easy to count the apostrophes. Your eyes can just look at that and see there's 2 apostrophes. But imagine if I wrote 7 of them, and you'd have to squint your eyes and look really closely and count, then it would be easy to make a mistake. So that's why we just prefer to write the number with brackets around it. The analog of this, we would just replace the 2 with an n. So you get dny over dx to the n. So that's the nth. Take the nth derivative of y with respect to x all n of the times, or take the nth derivative of y with respect to x n times. That's another way to say it. And just like in the case above, you can pull the y off of the operator and write it in operator notation, and you get dn dx to the n of y is equal to dn dx to the n of f of x. Those are 5 ways to write the nth derivative of the function f, or of the function y, whatever you want to call it. So these all mean the nth derivative. Let me put all mean the nth derivative, just to be clear. And same over here, these all mean the second derivative. Okay, so that's higher order derivatives. We won't work with them too much just yet, but it's good to know that they exist, and we will definitely work with them in chapter 4, a little bit in chapter 3, but we'll really get to apply them in chapter 4. But I just want to expose you to them early, so you've seen them, so they don't seem brand new when we look at them later.